let us start. So, okay, yeah. So today we have the pleasure to listen to Loïc Foissy from Calais, and the talk will be about double bialgebra of non-crossing partitions. Please.
Okay, so thank you for the invitation, and thank you, Dominic, for this introduction. So I'm going to talk about non-crossing partitions. So I will start with showing what they are and give a motivation from probabilities. Then I will introduce what are double bialgebras, what consequences you have if you have a double bialgebras, and then application to non-crossing partition. And this will give strange families of polynomial, which I don't really understand, but maybe you will have some ideas about them. So what are non-crossing partitions? These are partitions of an integer, set partitions, and they are non-crossing. So this means, for example, you cannot have 1 and 3 in a block and 2 and 4 in another block. This would give a crossing, and represent them like this. So you saw this sort of grafting of graphs. So for example, for this one, there are 2 blocks, 1, 3 together, and 2, and there is no non-crossing. So you represent them by graph with legs. The vertical edges are legs, and horizontal edges represent the blocks. So there is one non-crossing partition of size 1, 2 of size 2, then 5, and 14, then 42, and so on. In fact, the numbers is given by Catalan numbers. I will come back to them later. So a motivation to study this non-crossing partition. I start with a random variable, a classical random variable in probability. But you can't compute its moment for all n. This is the expectation of its powers. So sorry, x to the power n, the n should be up and not down. Sorry for this. You assume that this exists, and in fact, if x and y are independent random variables, then you know that the moment, the nth moment of the product xy is the product of the nth moment of x and y. In good cases, at least if all these moments exist, you can determine the law of x and y, x plus y, if x and y are independent, thanks to its moment. You can compute the moment of x plus y just by a binomial formula. So this is the classical case. So, sorry, first you have a variance, which is the moment of order 2 minus the square of the moment of order 1. And you know, which is quite classical, that if x and y are independent, the variance of x plus y is the sum of the variances. So it's really more complicated if you take non-commuting random variables. For example, you can think of random variables which take values in matrices. In fact, infinite matrices, something very big. And for this object, the classical notion of independence is not the good one. This was shown by Nika and Spasher. And they defined a notion of free probability, which is really more useful for this sort of objects. It turns out that it is really difficult to define with moments, and they introduce something else, which is called the free cumulants, which are associated to random variables. In fact, cumulants are related to moments by this sort of formula. So to see, the nth moment is defined as the sum of our own non-crossing partition of a product of cumulants. I will detail this formula in the next slide. And under reasonable conditions, so this means that at least the moments should exist for all n, then x and y are fully independent if or only if, for all n, the nth cumulant of x plus y is the sum of the nth cumulant of x plus the nth cumulant of y. So in free probabilities, non-crossing partition really appears like this with this relation between cumulants of moments. So I detailed these relations. So for example, for 3, you have 5 non-crossing partitions. So this means that the third moment is the sum of 5 terms, 1, 3, plus 1. So this term, it has 3 blocks of size 1. So this contributes to k1 to the power 3. this has only one block of size 3, so this contributes to K3, and these three non-crossing partitions have one block of size 2 and one block of size 1, so they contribute to K1, K2 3 times. And the same for this, you have 14 terms, 6 for this, K1, 2, K2, because you have 6 non-crossing partitions with a block of size 2 and 2 blocks of size 1. In fact, they are here, and so on. So I rewrite these relations. It's exactly the same. And you can observe, it's quite easy, that in fact, you can inverse this system. It's triangular in some sense. And you can find some formulas for the nth cumulant in function of the moments, the nth moment and the smaller moments. And in fact, these relations are known to depend on the Hopf algebras. In fact, if you do something like this, it is an inversion of a character for the convolution product, which is associated to a quite complicated coproduct. So something in there, you have a Hopf algebra, which I'm going to present in a few minutes, and an inversion, a computation of an antipode. So if you have some question, do not hesitate to interrupt me. So this was for the motivation from three probabilities. And now I'm turning to bialgebras and double bialgebra. So I start by quite a classical object. You take an algebraic group, or if you want to be a little bit more general, an algebraic monoid. So what does this mean? In fact, you have a monoid with a topology, which is quite special because this topology allows you to define polynomials on your monoid. So you have an algebra of functions, which are the polynomial function on J, and you define this algebra as C of J. Proto-algebraic means that, in fact, you can work with infinite dimensional objects. Usually, for algebraic group, you restrain to something which is finite dimensional, but you can extend a little bit with some conditions. So you can have some infinite dimensional objects. So of course, this algebra only reflects the topology of the monoid. You want to represent the product of the monoid in some sense. So a good way to do this is something like this. You take a function, a polynomial function on J, and you turn it into a polynomial function on J times J. So f is defined on J, delta of f is defined on J times J by this formula. So delta of f reflects the product of J. So if the group, if a monoid is correct with this topology, in fact, this defines a function on J times J, and it should be polynomial. So you have an object on this algebra, and again, if everything is okay, this algebra is in fact identified with Cj tensor Tj. So this is a bialgebra. This is an algebra equipped with a coproduct delta, which goes from Cj to Cj tensor Cj. And again, if your group is algebraic, everything works, and you really obtain an algebra morphism from Cj to Cj tensor itself. Well, you can consider this object with this coproduct, and it turns out that you can go back to the monoid, considering its character. So a character of a bialgebra is just an algebra morphism from B to the base fit. And in fact, in algebraic case, this set is in bijection with elements of J. This is the Null-Channel Satz, in fact. And because you have a coproduct, dually you obtain a product on characters, given by this formula. You take two characters, you apply it on an element of J. So you first apply delta of J, then you apply the characters on the left, on the right, and then you multiply in C, and you obtain a new character. And in fact, in the good cases, this monoid, which you obtain, is isomorphic to the monoid we started with, J. So if your monoid is a group, again, with algebraic structure, polynomial function on this and something like this, then maybe you want to consider the inverse in J. So this gives you a map from J to J, big J to big J, which should be polynomial in some sense. Then you can transpose it from Cj to Cj. So you take a function, a polynomial function on J, you transform it into another polynomial function on J, just by applying f, not on x, but on the inverse of x. So this gives you another structure on C of J, on this algebra, which is called the antipode, with good properties. You can think that, for example, you know that the inverse of GH is the inverse of H times the inverse of J. And this can be translated into the fact that S is an anti-algebra morphism, for example. When you obtain a lot of properties like this, a bialgebra with an antipode is what is called a Hopf algebra. And usually, if you have a Hopf algebra, then the monoid of characters, in fact, is a group, and the inverse is given by the antipode. So I want more structure on my monoid, J, and maybe J is a ring. You can think of C, the base field C, complex numbers, with addition and the multiplication. This is a little bit too restrictive for non-crossing partitions, so I will assume that J has two products. Well, it has a sum and a product, the plus and times, which are both associative and unitary. So you have two units, which I denote by 0 and 1. It's not really surprising. I do not assume that the multiplication is distributive on the addition. I assume only it is distributive on the right. In fact, this is what I will have for non-crossing partition. It's only distributive on the right, not on the left. And I do not assume that the addition and the multiplication are commutative. So how can you translate this? Well, you should have a polynomial algebra on J. So you have an algebra B, which is the polynomials on J. If everything is okay, if the topology is correct or something like this, you can dualize the two products, the addition and the multiplication, and you obtain two coproducts, big delta here and small delta. Big delta corresponds to the addition, small delta to the multiplication, with good conditions. So both should be algebra morphism. Both should be co-associative. So what does it mean? In fact, a coproduct should be understood as something which take an element of B and cut it into two parts, maybe in several ways, possible, but essentially a coproduct take an element and cut it into two parts. If you want to take an element and cut it into three parts, you can do it into two ways. First, you cut it into two parts with the coproduct. You can cut the left part or the right part. So you apply the coproduct on the left or on the right. And, well, you should obtain the same thing, which is exactly what means these two relations. I mentioned that both products have a unit. So dually, both coproducts have a co-unit, which are denoted by epsilon, big delta, epsilon, small delta. So a co-unit is in fact a linear form on B. So this is something which goes from B to the base field C. You obtain something like this. Here, delta, you take an element of B, you cut it into two parts. You apply a linear form on the left part. So this means that in some sense, you kill the left part. And what you obtain is what you take at the beginning. And the same on the right for both co-units. So this was just the translation that plus and times are monoids. You want to translate the fact that the multiplication is right distributive on the addition, and what you obtain is exactly this relation. So this is exactly the translation of this. So what does it mean? You cut an element into three parts. First by the product on the the product, and then by the addition on the left, or you can cut it into two parts with the addition, cut each part with the multiplication, and reunite together the second and the fourth part to obtain only one element. And this is exactly what is a double bialgebra. In fact, if you want to have an image of a double bialgebra, this is something which a monoid of characters has two products, and the second is distributive on the right on the first one. So a simple example, well, I start with something with two structures, which is just C, with the addition and the multiplication. Polynomials on C are just classical polynomial in one indeterminate, which I call x. So x is in fact the function from C to C, which is the identity of C. And you can dualize the addition and the multiplication, and you obtain two coproducts on C of x. So what means this formula? If you want to compute delta of xn, what you want to compute is x plus y to the power n. You know you can develop it with a binomial formula, and you obtain exactly this formula. For the product, what you compute here is xy to the power n, which is xy times yn. Xn times yn, sorry. So you obtain exactly this. The unit of the addition is 0, the complex number 0. So the co-unit is the evaluation in 0. The unit for the multiplication is 1. So the co-unit for the second coproduct is the evaluation in 1. And this is really a double bialgebra. This is maybe the simplest possible double bialgebra, except the base field itself, which is not really interesting. So you can simplify this definition of the two coproducts because you know that both coproducts are algebra morphism. So in fact, it's enough to define them on X, something like this. And well, this is simpler to define the coproducts like this rather than these two formulas. In particular, if you want to show that delta is co-associative, you can show it on X only and not on this big formula. So now I change my point of view. Till here, I had a monoid with two products, and I defined an object, an algebraic object, a bialgebra on it. Now it's the other way. I will have a double bialgebra, which I define mostly with combinatorial objects. And then I know that I will have a monoid with two products and a good distributivity of the second product on the first one, and so on. I don't know exactly what these groups are. I know that they will be very huge, but in fact, it does not really matter. What interests me is the half algebra or the double bialgebra. And if I understand the double bialgebra structure, I know that I will have some result on the characters. So my first combinatorial example will be on graphs. So I take a vector space, which has for basis the set of all finite graphs, so something very huge. There are a lot of graphs. And with a very simple product, which is the disjoint union. So, okay, for example, this is a disconnected graph, and in fact, this is the product of a graph with a single vertex times itself, for example. So the product is very simple. The unit is just the empty graph, okay? And I can define two coproducts, so something like this. For this, I want to find a way to decompose the graph into two graphs. Well, I choose some vertices which I put on the left and the other vertices on the right. And well, this gives me two graphs. So for example, for this, I can put all the vertices on the left. This gives you the graph. On the right, you have nothing, the empty graph, one, or everything on the right. I can put these two vertices on the left. What I obtain on the left is a graph connected with two vertices. On the right, only this. I can do the same for the other edge. I obtain the same term, so you will obtain a coefficient 2. Or I can put on the left these two vertices. I obtain a disconnected graph, and on the right, I put the remaining vertex, which go for this. Or I can choose to put two vertices on the right and one vertex on the left. It gives you the same term, but flip from left to right. So the first coproduct is rather simple, just cut your vertices into two parts. For the second coproduct, it's much more complicated. In fact, what you do on the left is to contract some edges. So for example, for this one, I can contract all the edges. On the left, I obtain something like this. I can contract one edge. On the left, I obtain something like this. The other edge, something like this. Or nothing, which I obtain something like this. And on the right, I just keep the edges I have contracted. So for example, here, I have contracted the two edges, so they appear here. Here, I have contracted this edge, it appears here, and this vertex remains alone, and the same for the other one. And here, I didn't contract anything, so here, I just have the vertices and no edge. So this is a double bialgebra. This is not very difficult to show that the first coproduct is co-associative. For the second one, it's a little bit more subtle. What you do, in fact, is if you iterate the coproduct on the left, you have to consider contractions on contraction and so on, or something like this. And maybe the most tricky part is to show this relation, so this one. What does it mean? First, you take a graph, you contract on the left and you delete some edges on the right, and then the contracted graph is cut into two parts. This is the same as cutting your graph into two parts, contracting on the left and on the right, and then reshape everything together. So another example, which is also rather classical now, is based on rooted trees. So this is maybe more famous than the first one. This Hopf algebra, this first coproduct, is known as the Butcher-Cohn-Kramer coproduct. I think it was really described as a Hopf algebra by Cohn and Kramer at the end of the 20th century. And then it was discovered that, in fact, this Hopf algebra was related to a group described by Butcher, which was based on the Runge-Kutta method. Unfortunately, Butcher's did not seem to know the formalism of Hopf algebra, so his description was purely combinatorics and rather difficult to read, I think. And maybe 10 years later, Damien Cala, Kourouche, Ebrahim Ifart, and Dominique defined another coproduct given by contraction of edges on it, and they show that this is a double bialgebra in the sense I described just before. So how does it run? For the first coproduct, you can cut some edges. So you have to imagine this as a real tree, subsets, with a root, which is at the bottom, and you cut some edge, and a part fall, which is the branches, and you put them on the right. And on the left, a trunk remains, which is put on the left. For example, here I didn't cut anything. Here I cut everything. Here I cut a leaf, this one or this one, so you have a coefficient 2. And here I cut the two leaves, and you get something like this. Here I can cut nothing or everything, or I can cut here, or I can cut here, something like this. And the second coproduct is also given by contraction of edges. So for example, for this, I can contract this edge, I obtain something like this, or this edge, I obtain something like this, or both edges, I obtain something like this, and the edges I have contracted goes on the right, which is quite similar to the graph, in fact. So this is a double bialgebra also. These are maybe the most famous examples, and now I'm going to give a double bialgebra on non-crossing partitions. So in fact, it's a little bit more complicated because it's not a non-crossing partition, but on monomials of non-crossing partitions. So my algebra here is the free commutative algebra generated by the set of non-crossing partitions. So this means that you have to consider each non-crossing partition as an indeterminate. You can consider all monomials in these indeterminates. So there is a technical difficulty because you have some notation like this. This is a non-crossing partition of size 2 with 2 blocks of size 1. But this is not a product. And if you don't want to confound them with a product, you have to denote the product by a dot like this. So this is a non-crossing partition. This is not a non-crossing partition. This is a product, a commutative product of 2 non-crossing partitions of size 1. So these are different. These are different because there are 2 different non-crossing partitions. These are different because this is a non-crossing partition. This is a product of 2 non-crossing partitions. The same for this. And the product is commutative. So with a dot, the order of the indeterminates does not matter. So for the first coproduct, well, I say I want to cut my non-crossing partition into 2 parts. There is an easy way to do this. You choose some block. You choose some blocks. You put them on the left, and the other blocks will go on the right. With a constraint, there is a notion of nesting on non-crossing partition. So, for example, this block is nested into this one. And if you choose to put a block on the right, then all the block which has nested in it should also be on the right. So for example, for this, you can put all the blocks on the left or all the blocks on the right. And this block on the right and this block on the left, it gives you this term. But you cannot put this on the left and this on the right because this block is nested into this one. So it is not possible to put this on the left and this on the right. So for this, there is no nesting. So you can put everything you want on the left and everything you want on the right. But there is a subtlety you can show here in red. For this, for example, I choose to put these 2 blocks on the right. What you obtain on the right is this, and on the left, well, it remains only 1 block. You can put all these 2 blocks on the right. It gives you this also, so coefficient 2. And on the right, it remains only 1 block, this. Or you can choose to put this and this on the right. But these 2 blocks are separated by another block. So this does not give a non-crossing partition, but a product of 2 non-crossing partitions of size 1. So if you separate this and this on the right, they become a monomial of 2 non-crossing partitions with a dot. So in fact, this coproduct reflects the relation between moments and cumulants. So this is why this coproduct is interesting. And the co-unit is very simple. In fact, it's 0 on all non-crossing partitions. For example, if you apply this on this one, on the left, this goes to 0. So this goes to 1, so it remains this. 0, 0, it only remains this, which is the same non-crossing partition. So for the second coproduct, what you can do on the left is to melt together, in some sense, to give a fusion of several blocks. So for example, for this, I choose to do not do any fusion on the left. So you have 2 blocks which are on the right. And you can do the fusion of the 2 blocks. So on the left, the 2 blocks gives only 1 block, something like this. And these 2 blocks goes on the right. For this, you can do any fusion you want, in fact. So you can do no fusion. You can fusion these 2 blocks together. It gives you this. Or these 2 blocks together. It gives you this. Or the third on the first and the third block, something like this. Or the 3 blocks together, and something like this. And well, it gives you a second coproduct, and this is a double bialgebra. So the most tricky part, if you want to show this, is the compatibility between the two coproducts. So if you want to show this, what you do, you can first separate your non-crossing partition into an upper and a lower part like this, and then do fusions on both parts. This is the left side on the compatibility, or you can do the coproduct like this and separate the fusions on the left into two parts, an upper and a lower part. This is something like this, and you can observe that this is the same thing. So this is really a double bialgebra. So, okay, this is fine. You have an interesting object. Well, what can you do with this? So now I'm going to describe some theoretical results on double bialgebras. So first, in most cases, what really interests you is not the whole structure, but only the first one with the first coproduct. And maybe you want to compare it with a simple or simpler object, maybe polynomials or something like this. So this means that you want to find some bialgebra morphism for the first structure to another one, which is denoted by prime. So this defines a set of bialgebra morphism from Bm delta to B prime and prime delta prime. This is not just a set. In fact, the monoid of characters of the second coproduct acts on it. So you can take a morphism phi from B to B prime, a character lambda. So this goes from B to the base field C. And you can transform it into another bialgebra morphism. You take the second coproduct, then you apply phi on the left, lambda on the right. Of course, so delta goes from B to B tensor B, phi goes from B to B prime, lambda goes from B to C. So this goes from B to B prime also, and this turns out to be another bialgebra morphism. So what does this mean? In fact, if you manage to define, if you manage to define a bialgebra morphism for the first coproduct, in fact, you obtain a lot of bialgebra morphism just by the action of characters. So this means that you have a mean to deform any morphism you want just by the action of a character. So for the second bialgebra, I take just polynomials. So what you can think of it, you can consider graphs or posets or non-crossing partition, and you want to associate to them a polynomial invariant. Maybe you can think of chromatic polynomial for graphs or something like this. And if your polynomial invariant is correct, this means that it should be compatible with the product and the first coproduct. So what you can prove, you choose B prime equals C of X, you need a technical condition I will give later in the next slide. If you want to obtain a morphism which is compatible with the product and the two coproducts, well, there is only one, a unique phi 1. So there is a unique polynomial invariant which is compatible with every structure you have. And this will be called the fundamental polynomial invariant. And if you want to obtain other morphism from B to C of X, well, you know for sure that they will be not compatible with the second coproduct, but we can show that you will obtain everything just by the action of characters. So you take your fundamental invariant, you can deform it by a character. This gives you a bijection. And for inverse bijection, you just take your morphism and you evaluate into one. That's all. So this means that in these cases, if you find the fundamental polynomial invariant, in fact, you can describe after all the polynomial invariants. So the question is how to describe this fundamental polynomial invariant. Well, you have a formula, something like this. You take an element of B, you can cut it into one part, just taking X, two parts, three parts by just iterating the coproducts. This is the reduced coproduct, so this means that you forget the primitive part. So maybe, for example, for this, you observe that there is always a primitive part, the non-crossing partition tensor 1 plus 1 tensor non-crossing partition, all these terms, and maybe something else. Well, this is not really interesting. Just keep this and then iterate. So you take X, an element, you cut it into n non-trivial parts. You apply some scalar, you transform them by scalars just by applying the counit for the second coproduct. So this gives you a scalar, and you multiply this scalar by a Hilbert polynomial. So the technical condition of connectivity just means that this, for any x, should become 0 if n is great enough. So the connectivity condition, it is mentioned here, just means that in fact for any x, this sum is finite, so this really has a meaning as a polynomial. Let's do it for graphs. So what does it mean? I applied this formula. X is now a graph. Here, this means that I cut the vertices into all possible parts, into nth part in all possible ways. I apply a character on all these parts. So this character is 1 if the graph has no edge, and 0 if the graph has edges. So this means, in fact, for this, I cut my graph into nth part, and each part should not have any edge. So this is, in fact, related to the classical notion in graph theory of admissible colorings. And this implies that this fundamental invariant is just the chromatic polynomial of graphs. So this counts something like this. This is the number of colorings. So the coloring is just a map from the vertices to a set of integers, for example. And if you have an edge, then the two vertices should have different colors. And for rooted tree, this is something similar, which is called the strict Erhard polynomial. In fact, the same, you color the vertices of your tree, such that if you have an edge in T, well, the edges are oriented from the root to the leaf, then the lower vertex should have a smaller coloration than the upper vertex. More results on double bialgebra. I mentioned that if you have a bialgebra, you have a group of characters, and the inverse is given by the antipode. So if you want to consider some inverse, you want to do this if you consider an encrossing partition and three probabilities. Well, you need a formula for the antipode, and usually it's not so easy to compute. There is one case where you have a formula, at least, this is the Takeuchi formula, under the same condition, and it's quite similar to this, in fact. It is an infinite sum for any x of iterated coproducts. So here I just apply a character on all parts. Here I just multiply all the parts together. And then I multiply with the same. And I take all the possibilities. So at least this formula exists, but practically it's not so convenient. I'm going to give an example. So for example, for polynomials, I apply this formula for x3 and x4. What does this mean? I cut x3 into one way, two ways, three ways, etc. and so on. So into one block, this is just x3, is a thing. If I cut it into three blocks, this gives you x2 three times, x2x three times. If I cut it into three monomials, you obtain x six times. Into four monomials, it's not possible without any trivial monomial. So we stop here, you obtain this sum, and at the end, you just obtain x minus x3. So for x4, similar, you can cut it into one part, one monomial, two monomials, so x3, x3x, or x2, with coefficients, into three monomials, x2, x2x, x2xx, with coefficients, or xxxx, four times, with factorial coefficients. And at the end, you just obtain x4. So the Takeuchi formula works, but practically, even for this example, it's not really not optimal. So it's better if you have a double bialgebra. So what you have to do, so remember the antipode gives you the inverse of any character. With a double bialgebra, you have to compute it only for one character, which is the co-unit of the second coproduct. If it has an inverse, alpha, then you have the antipode like this. You apply the second coproduct, and you kill the left part with this special character, alpha. Well, how to find alpha? If you know what is the double bialgebra morphism from B to C of X, the fundamental polynomial invariant, if you want to compute alpha, you just take phi 1 and compute it into -1. And this gives you the inverse of this unit. And then you obtain the antipode, which is related to the fundamental invariant, fundamental polynomial invariant taken into -1. So, okay, this is nice. It's not so easy practically. You can maybe think of graphs, I gave before. For graphs, the fundamental invariant is the chromatic polynomial, and it's not so obvious to find what is counted by this chromatic polynomial evaluated in -1. So if you don't know the result, it's quite hard to find. In fact, it counts the acyclic orientations of graphs. So for graphs, the antipode is related with acyclic orientations. So, okay, I apply all this stuff to non-crossing partitions. So I want to compute the polynomial invariant, fundamental polynomial invariant. So I know that with this formula, this one, I have to iterate the coproduct. So what does it mean? For the coproduct, I separate the blocks into a lower part and an upper part. So I iterate it. This means that I separate the blocks into a lower part, a second part, a third part, and this part should be nested. So this can be represented by something like this. For each block, I give an index, which gives you its place in this tensor. And if you have a nesting, if B prime is nested into B, well, if B is on a part, B prime should be more on the right. And so this should be B and B prime, not P and P prime. I will correct this later. So this is the coproduct. If you want to reduce this, well, you have to forget about the trivial part. So this means that you replace all maps by all surjective maps. So this is the sum of all surjective maps on blocks with the same condition. Then you will have to apply epsilon delta for the second coproduct on all these blocks. And the Q-unit is 1 if the non-crossing partition here is a monomial of non-crossing partition with only one block and 0 otherwise. So if you put this all together, what you obtain is something like this. So the fundamental polynomial invariant for non-crossing partition counts something which is described like this. This gives, or you evaluate it into n, which is an integer. You count the number of maps which to each graph associate a color. If you have a nesting, then it should be increasing on this, strictly increasing. If you have two blocks with the same color, fb is equal to f of b prime, then you know that they cannot be nested because of this. So one is on the left and the other is on the right. So this condition means that fb is on the left and B is on the left and B prime is more on the right in the graph of the non-crossing partition. Then these two graphs should be separated, these two blocks should be separated by another blocks, B second. So this means that this block is between B and B prime, and its color should be smaller. So this is quite a classical condition. this is related to error condition or things like this. This is really more strange. So, well, you have an combinatorial interpretation of this fundamental polynomial invariant. It's not so easy to compute, but you can do something like this. In fact, you have an induction which allows to compute it. So take a non-crossing partition, so this should be P and not pi. You evaluate phi1 of P into n plus 1 colors. So this means that you take the colors 1 to n, and then you add a new color, which I call 0. Maybe you won't use this color. So you obtain just coloration with n colors. So this gives you the term phi1 of P. If you use the color 0, well, you have something like this. So the color 0 should only be on the base. So these are the minimal elements for the nesting. Moreover, if you have two elements with the same color, so the same color 0, should be separated with a color whose color should be smaller than 0, but this is not possible. So in fact, if 0 appears, it only appears on one element of the base. So if you imagine a non-crossing partition, you choose an element of the base, you delete it, and your non-crossing partition fall into three parts, which is on the left of your element B, on the right, or nested in B. So this is exactly the signification of this formula. So this is exactly what I just explained. If you take a valid coloration of P, the smaller color is it does not appear, or it appears only one on an element of the base. So this allows to compute this polynomial. It starts to be interesting for example, for this. You obtain things you wait, in fact, x minus 1, x minus 2. This is, you knew before that we will have this. What is more surprising is the last factor, which is x minus 4 over 3. I don't know what this means exactly, this 4 over 3. I just found it, in fact, by computation. So now I want to compute the antipode, and this is important because this is related to the formula which relates moment of cumulants. So I would like to compute the antipode for the first coproduct. So what I know is I have to take the fundamental polynomial invariant, phi1 of x, take it in minus 1. This gives you a character, which I denote by mu. And for the antipode, I just have to compute the coproduct. So separate the blocks into parts and then do some fusion on the left, and then to apply mu on the fusion. So the problem is to compute mu on any non-crossing partition on minus 1. So we can do this something like this. Well, you take x is equal to minus 1. This gives you phi1 of p of 0. So this is 0. This is what you are looking at, mu of p, and this is an induction. So you can compute mu on an induction, by induction, and in fact, it turns out that it's only it's enough to compute it on non-crossing partition, which are realistic, with no nesting, so non-crossing partition, which is restricted to their base. So in general, you can compute it inductively like this. Then you have to compute this something like this. So for a non-crossing partition, which is restricted to its base, so with no nesting. And this is an induction. In fact, you will obtain back Catalan numbers. So I give a reminder what are Catalan numbers. They are given by this formula. You have the first values. There are very famous numbers. They count a lot of things, including non-crossing partition, but also planetaries, parenthesis words, and really a lot of stuff. Well, here I'm interested only on non-crossing partition. In fact, the antipode is given in some sense by Catalan numbers with things. Let's do an example for this. You want to compute the antipode of this simple object, non-crossing partition with 3 blocks. I compute the coproduct. I've already given it before. And then I apply mu on the left part. So for this, this is something with no nesting. So I know that its value is the Catalan number, is -5. The same for this, there's only one block. This is the first Catalan number, 1 with a thing. And for this has 2 blocks. It gives you the second Catalan number, 2. 2. This has a nesting, so this gives you a product of Catalan number, which is 1 times 1. So the 5 here is not a Catalan number. It's 2 plus 2 plus 1 times 1. And generally, what you will obtain is coefficients which are given by Catalan numbers and product of Catalan numbers. So I think I have time to give more details on this fundamental polynomial invariant. And in the most complicated case, in fact, is given by non-crossing partition with no nesting. So they are restricted to their block basis. What you can show quite easily is that in this case, it only depends on the number of blocks of P, not of the size of blocks. So for each number of blocks, you obtain a polynomial, which I denote by phi indexed by k, and you obtain a sequence of polynomials, which you can compute. So it gives you these strange polynomials. The only clear coefficient is maybe the leading one. So you observe quite easily this is the polynomial of degree n, and which is unitary. But even the coefficient of x is rather complicated for 6. This is 157 over 15. It is quite a mysterious number. There is a way to compute it. So this you can do with the induction I gave before, but this is not really easy to do this. There is another way with an infinite matrix given by this coefficient. So a matrix called with a binomial coefficient. So this gives you an infinite matrix M, which is triangular. So you can do some computations on powers of M. It's not a real problem. And you can even do some formal series of M. For example, this one. So this is a formal series with a power X. So this gives you an infinite matrix, which is a triangular with X in all these entries. And in fact, this sequence is in fact the first row, the first column of this matrix. So this matrix M is not, it's quite particular. In fact, it is a Raynordan array of these 2 formal series. I recall maybe what is a Raynordan array. In fact, I didn't know before I worked on this. I have to say this. This is a group of infinite triangular matrix. You take 2 formal series. You can compute P times Q to the power L. So L should be of order 1 without any constant term, and take the coefficient of Tk. This gives you a group of infinite triangular matrices, which is related both to the product of formal series and to the composition of formal series. In fact, this is a sort of a cross product of these 2 structures. And what you obtain is something in this group for this very simple formal series. So these polynomials are very combinatorial by nature. They count something. So maybe a good idea is to develop them in the basis of Hilbert polynomials. In fact, if you remember well, they were defined at the beginning in this basis. So we'll obtain some coefficients you can compute. Here they are. So what you can observe, this is triangular. Okay, this is not really surprising. The diagonal is easy. These are just factorials. And these just reflect the fact that these polynomials were unitary. So because there is a factorial n here, you will obtain a factorial here. You can also show that on each row, this is finite. So we start, it stopped at 1. 3, 7, and so on. And in fact, this is related to powers of 2. This is not very difficult to find. Generally, this coefficient does not seem to be very well known. For example, well, I found some of them, but for example, not this one, this big one. If you look at it in the encyclopedia of integer sequences, you do not find it anywhere. So this numbers does not seem to appear in any other context. This is rather strange for me. But anyway, you can find some formula. Maybe not in all possible cases, but it's easier. It's easier on the diagonal. So for this is the factorial. I'm going to give a formula for the next diagonal, the other one. For this, you need iterated harmonic sums. So the first is finite harmonic sums. So the first one is just the sum 1 plus 1 over 2 plus and so on plus 1 over n and so on. And you can prove this formula just by induction. For example, what is over the diagonal, so this sequence, 0, 1, 10, 86, 756, is given by this formula. So you obtain a factorial, a polynomial, minus an harmonic sum. You can do the same for the second subdiagonal, 0, 0, 8, and so on. This gives you by an harmonic sum, an iterated harmonic sum of depth 2, an harmonic sum times a polynomial plus a rational fraction. So how did I obtain this? I managed to obtain some induction for this formula, which I solved. This is rather tedious and technical, I should say, but you obtain something like this, and this strange fraction appears by itself. In fact, it seems to be true for any subdiagonal, but the formulas are worse and worse, so I stopped there. It seems that you can describe all these coefficients with harmonic sum, iterated harmonic sums, and polynomials and rational fractions. Here are some references. All this stuff are on the archive. I stop with thanking you for your attention. So thank you very much.
Thank you very much, Loïc, for this very nice talk. There's a question in the chat. Can you put the reference slide back up, please? Yeah.
Okay, this I can answer, yes.
Okay, so are there other questions about Loïc's talk? Sorry. No. Okay, so I may have a rather naive question. If you look at all the partitions, including the crossing ones, I think the constructions breaks up quite a lot. Can you say something about?
I know this is possible.
Yeah,
We didn't do it because we had in mind three probabilities.
yeah, of course, yes.
For crossing partition, you have to do some choices for the first coproduct.
Yeah.
Do you allow to separate nestings and things like this? There is a notion of nesting also for crossing partitions, and it's not clear what to take.
Okay.
But I think there is something related to classical independence with a Hopf algebra of all partitions, including the crossing ones, and a structure like this. It's probably less interesting because, well, for classical probabilities, the formulas are easier than for non-crossing for free probabilities. I'm not totally sure.
Yeah.
We didn't check, but I'm quite sure that this exists.
Okay.
And probably they should be related to the Fadi-Bruno and something like this of algebras.
Okay.
In fact, well, maybe you just obtain the algebra of symmetric functions, something like this, or something very close.
Okay. Okay, are there other questions? Okay, so if not, we can thank Loïc again. Thank you very much.
Thank you.
And so I guess there's a talk next week. You can you will get the announcements in due time, I guess. Okay, thank you very much.
Thank you.
Bye now.